Hi, Stu Schwartz from MasterMathMentor.com. This is video BC Non-Essential 2a. The topic is integration with powers of sines and cosines, and it covers the BC manual pages 146 and 147. Suppose we were asked to find the integral of sine cubed of x dx. We could do this with integration by parts. We let u equal sine squared of x and dv equals sine of x dx. Therefore, du equals 2 sine of x cosine of x dx, and v is equal to negative cosine of x. So by our integration by parts formula, this integral becomes negative sine squared of x cosine of x plus 2 the integral of sine of x cosine squared of x dx. We now use u substitution to find the integral. U is cosine of x, du is equal to negative sine of x dx. So our expression becomes negative sine squared of x cosine of x minus 2 cosine cubed of x over 3. That solution is sufficient, but usually we would prefer our answer with one trig function rather than two, and also in factored form. We can do that. We will change the sine squared of x to 1 minus cosine squared of x, and we get negative quantity 1 minus cosine squared of x times cosine of x minus 2/3 cosine cubed of x. Multiplying out, we get negative cosine of x plus cosine cubed of x minus 2/3 cosine cubed of x. And factoring out, we end up with cosine of x over 3 times the quantity cosine squared of x minus 3 plus c. There are 3 guidelines to integrate expressions with powers of sines and cosines. First, if the power of the sine is odd and positive, save one sine factor and convert the other remaining factors to cosines. Then expand and integrate using u substitution. Second, if the power of the cosine is odd and positive, save one cosine factor and convert the remaining factors to sines. Then expand and integrate using u substitution. Finally, if the powers of both the sine and cosine are even and non-negative, make repeated use of the identities that sine squared of x is equal to 1 minus cosine of 2x all over 2, and cosine squared of x is equal to 1 plus cosine of 2x all over 2, to convert the integrand to odd powers of cosines, and then proceed as in Guideline 2. Here are 2 problems that illustrate Guideline 1. In problem 1, we're asked to integrate sine cubed of x dx. Again, this is Guideline 1. We pull out a sine x, and we have the integral of sine x, sine squared of x, dx. We can write sine squared of x as 1 minus cosine squared of x. And now we can split this into 2 integrals, the integral of sine of x dx minus the integral of sine of x cosine of x squared dx. The first integration is easy. The second uses u substitution, with u being cosine of x and du equals negative sine of x dx. So when we do our 2 integrations, we get negative cosine of x plus cosine cubed of x over 3 plus c. For this problem, we will check it by taking the derivative of negative cosine of x plus cosine cubed of x over 3 plus c. When we differentiate, we get sine of x plus, using the chain rule, cosine squared of x times negative sine of x. We can factor out a sine of x, getting sine of x times the quantity 1 minus cosine squared of x, and 1 minus cosine squared of x is sine squared of x. So we get sine of x, sine squared of x, which is equal to sine cubed of x. Number 2 reads the integral of sine cubed of x, cosine to the fourth of x, dx. This is guideline 1, as the sine has an odd power. So we pull out a sine and we get the integral of sine of x times sine squared of x times cosine to the fourth of x dx. We can rewrite sine squared of x as 1 minus cosine squared of x, and our expression becomes sine of x times quantity 1 minus cosine squared of x times cosine to the fourth of x dx. Multiplying out, we get the integral of sine of x times the quantity cosine to the fourth of x minus cosine to the sixth of x dx. Again, u is cosine of x and du is equal to negative sine of x dx. So this expression becomes negative the integral of negative sine of x, cosine to the fourth of x minus cosine to the sixth of x dx. And when we integrate, we get negative quantity cosine to the fifth of x over 5 minus the cosine of seventh to the x over 7. Final answer is cosine to the seventh of x over 7 minus cosine to the fifth of x over 5 plus c. We will leave the check, if you care to do it, to you. 2 more problems with odd powers of sines and cosines. In number 3, we're asked to integrate cosine to the fifth of x, sine squared of x, dx. This is guideline 2, as the cosine has the odd power. So we pull out a cosine and get integral of cosine of x times cosine to the fourth of x, sine squared of x, dx. And we can then write cosine to the fourth of x as cosine squared of x squared, which is 1 minus sine squared of x squared times sine squared of x. Expanding this, we get the integral of cosine of x times sine squared of x minus 2 sine to the fourth of x plus sine to the sixth of x dx. It looks difficult, but this is a typical u substitution with u equaling sine of x and du equaling cosine of x dx. So we integrate each piece and get sine cubed of x over 3 minus 2 sine to the fifth of x over 5 plus sine to the seventh of x over 7 plus c. In number 4, we're asked to integrate sine cubed of x over square root of cosine of x dx, and then integrate the same expression from 0 to pi over 3. This again is guideline 1, as the sine has an odd power. Do not be concerned that we have a square root of a cosine of x. That doesn't enter into it. So we write this as the integral of sine of x times sine squared of x over the square root of cosine of x dx. Writing the sine squared as 1 minus cosine squared, we have the integral of sine of x times the quantity 1 minus cosine squared of x over the square root of cosine of x dx. We can take the expression with the cosines and write them to cosine to different powers. So we have the expression cosine of x to the negative 1/2 minus cosine of x to the 3/2, that whole expression times sine of x dx. U substitution works here. U will equal cosine of x, and du is equal to negative sine of x dx. So when we do the integral, we get 2/5 cosine of x raised to the 5/2 minus 2 cosine of x to the 1/2 plus c. Doing the definite integral, we get 2/5 cosine of x to the 5/2 minus 2 cosine of x to the 1/2, evaluated between 0 and pi over 3. Using the fact that cosine of pi over 3 is 1/2, we get 2/5 times 1/2 to the 5/2 minus 2 times 1/2 to the 1/2 minus the expression 2/5 minus 2. So this is 2/5 times the square root of 2 over 8 minus 2 times the square root of 2 over 2 minus 2/5 plus 2, and this gives us 8/5 minus 19 square root of 2 over 20. You can integrate this expression on your calculator, get a decimal answer, and show that it is equivalent. In number 5, we're asked to integrate cosine to the 4th of x dx, and also the integral of cosine to the 4th of x dx from 0 to pi over 2. This is our first example of guideline 3, as there's only one trig function and it has an even power. We make use of the fact that cosine squared of x is equal to 1 plus cosine of 2x over 2. So the integral of cosine to the 4th of x is the integral of quantity 1 plus cosine of 2x over 2, quantity squared dx. And when we expand this expression, we can write this as 1/4 the integral of 1 plus 2 cosine of 2x plus cosine squared of 2x dx. Now, we can write this as 1/4 the integral of 1 plus 2 cosine of 2x, and we can write the cosine squared of 2x as 1 plus cosine of 4x all over 2 dx. So, when we perform the integration, we are looking at 4 different expressions. So we have 1/4 times the quantity x plus sine of 2x plus 1/2 x plus 1/8 sine of 4x. This uses use substitution several times. And that gives us 3x over 8 plus sine of 2x over 4 plus sine of 4x over 32 plus c. To integrate cosine of the 4th x dx from 0 to pi over 2, we have 3x over 8 plus sine of 2x over 4 plus sine of 4x over 32 evaluated from 0 to pi over 2. And this becomes 3/8 of pi over 2 minus sine of pi over 4 plus sine of 2 pi over 32 minus 0 plus 0 plus 0. And the only term that is non-zero is the first, and our final answer is 3 pi over 16. Again, you are encouraged to take this integral on the calculator to verify your answer, which of course will be in decimal form. Frequently in calculus, we have to integrate powers of trig functions from 0 to pi over 2. John Wallis, a 17th century mathematician, discovered 2 formulas which really help with this process and do not involve actually finding the indefinite integral first. If n is odd and greater than or equal to 3, then the integral from 0 to pi over 2 of cosine to the n of x dx is the same as the integral from 0 to pi over 2 of sine of n of x dx, which is equal to 2/3 times 4/5 times 6/7 times ... times n minus 1 over n. Now if n is even and greater than or equal to 2, the integral from 0 to pi over 2 of cosine to the nth of x dx is also equal to the integral from 0 to pi over 2 of sine to the nth of x dx, which is 1/2 times 3/4 times 5/6 times ... again times n minus 1 over n, but that is multiplied by pi over 2. So the integral from 0 to pi over 2 of cosine to the fifth of x dx by Wallis's formula will simply be 2/3 times 4/5, and the answer is 8/15. You can verify that on your calculator. The integral from 0 to pi over 2 of sine to the sixth of x dx by Wallis's formula is 1/2 times 3/4 times 5/6 times pi over 2. This gives 5 pi over 32, and again you can verify that on your calculator.